ready to go. Thank you all for coming, whether in person or virtually, if you're watching the recording. Today I'm gonna go through similar to how I did on the last test review I did for exam 2. I'm just gonna go through like all the different chapters, the different lectures that we have for the material on the last third of the class. So this is going to be like talking about chi-square distributions, confidence intervals, hypothesis testing, t-distributions, and regression. And that's what we're going to go over today. So I think Peter and Spencer, they did reviews for the first, third, and the second portion of the class. So feel free to go check those out. And you can also feel free to check out my review from last test too. Those should be all posted on Dr. Price's YouTube channel shortly. So how are you guys feeling?
Good. Yeah.
Good? Okay. So the test is cumulative. I think most of the tests, a good thing to study would be all this later half or later latter half of the material, but make sure you go back and study other units because you will be tested on those as well. And a lot of it kind of like adds up, it builds on each other. So I would make sure to go check those out. But today we're going to start with, let's talk about the chi-square distribution. So chi-squared. So basically, the chi-square distribution is a normal distribution squared. Pretty crazy. Well, it's your z squared, which we get from our normal distribution. So
that's a new one. I mean, that makes sense when you say it. I see it, but
yeah, it's pretty cool actually. And so it looks something like this. Forgive me if I can't draw very well. And a chi-squared distribution is gonna equal, like I said, your z squared if it's following a chi-squared. So basically this means that if z follows a normal distribution, then z squared is going to follow a chi-squared distribution. And those are standardized. 0, 1, mean variance of 0 and 1, and then your degrees of freedom is 1. So this v right here, if you ever come across a question that has like, I don't know, w follows, I think this was like on your homework, a chi-squared, and it has this notation. This number in the parentheses is v, which is your degrees of freedom. Degrees of freedom. And degrees of freedom is basically n minus 1. So the number of observations you have minus 1. And that's because you can look at Dr. Price's lecture notes for like the intuition, but it's basically because if I have a system of equations and I have 3 equations, right? If I solve for 2 of the variables, then the third one automatically is known. So I would have like 2 degrees of freedom, right? And that's the intuition behind it. So that's why we take n minus 1, because one of those observations or one of those data points is known if we know all the others. And I guess that's kind of the gist for your chi-squared. A few things to remember is the expected value of w, if w follows a chi-squared, is going to be equal to v, or the degrees of freedom. And the variance is equal to, does anyone know? It's 2v. So not too difficult. So this would be very useful to remember if you're asked a question about the mean or the variance of a chi-squared or a variable that follows a chi-squared distribution. So let's practice using the chi-square table, yeah? So,
Wait, in this case, it's B the variance or to be the degrees of freedom?
V is the degrees of freedom. This is like variance of W. This is degrees of freedom. So they're both V, but different V's. Yeah. Sorry that's confusing. And you can always write variance like this, but usually if you see like, I don't know, like V of some variable, it's the variance of that variable.
Do you know, if you take the two V and you put two V's together, then it makes it W. So which is like the chi-square.
Oh my gosh.
So
That's so true. Coming full circle here. Okay. So let's do some practice here. So say I have, say sales, I'm at some company and the sales, they follow chi-squared distribution, okay? And the average sales every month, we'll say, actually every week is 30, okay? What is the 10th percentile? Let's practice using this chi-square table. So if we pull up, if you go to Learning Suite, I apologize for those on the recording. I don't know if this will show up for you. But if you go to Learning Suite and
go into distribution help sheets.
you go to distribution help sheets, we can pull up this. No, that's not what I want.
Yeah, if you do that one, that works fine. And then you scroll down. That or you want to go to the lecture notes.
Yes, if you go to lecture notes, there's this, the tables. And I guess they're in the lecture notes and they're probably in that PDF, huh? But so there are several places in Learning Suite. So familiarize yourself with these tables. But let's practice using one of these tables. And so this is the chi-squared one, okay? So the way this table works, there's been some confusion around how to use this table. It's similar to the other ones, right? And what's very helpful is you get this picture here. It'll give you like a little picture up here if you can see. And if we look, it has, I guess for those on the recording, if you could pull this up. If not, this picture looks something like this, where this is all shaded in. This is labeled as alpha. And this number right here is your chi-squared sub alpha. So we're going to want to find, based on our degrees of freedom on this table, however much percentage or probability we want to lie above some point, right? Zoom in. So if I want to find the 10th percentile, what is the definition of the 10th percentile?
Wait, no, 10% is that 90% of the data is above?
Exactly. It's 10% is below and 90% is above. So I would want to find where my alpha is equal to what? Exactly, 0.9. So I'd come here and my degrees of freedom are what?
What's the sample size?
I'm told that the expected value of my sales or the average sales is 30 a week.
Okay.
So what would my degrees of freedom be? 29, exactly, right? Because the expected value of the variable sales, if it follows a chi-squared, is just equal to the degrees of freedom, or V. So it would be 30, not 29. Sorry. Did you catch that?
Yeah, 29 would be
29. This is if I was given like the number of observations, right? If I wanted to find degrees of freedom. This is giving me the average sales or the expected value of sales a week.
Value is just the direct amount of degrees of freedom.
Yeah, if you remember over here, the expected value of W, if W follows a chi-square, is the degrees of freedom, is V. And n minus 1 can also equal V. But it depends on the information we're given. So make sure you don't make that mistake. Usually you'll be able to kind of tell because on your table,
If it's not obvious, I'll just write down both and write down my assumption.
Only one will be right. But it will always be true that the expected value of W, if it follows the chi-squared, is equal to the degrees of freedom. Right? And if you remember when we'll get to it when we do our hypothesis testing with variance, we use a chi-squared, right? And when we use our test statistic, we have n minus 1, right? And that helps us determine the degrees of freedom, similarly with the t-distribution. So it's depending on the information you're given. So here we're given the expected value of our variable of sales. So we know that we want to find 30 degrees of freedom on here, and we want to find this sub 0.9, chi-squared sub 0.9, because we want 0.9 probability to lie above this point, which is the 10th percentile. So if we do that, we get 20.5992, yeah? And that would be our answer. So one thing that might confuse some students, and you guys probably have it down by now since we've been doing this the whole semester, but just make sure to remember what you're dealing with, right? This under the curve is the probability, right? This value right here, for example, or 20.5992 is the value that X can take on or W can take on. So you have some random variable and it's measured along this PDF. This is a PDF, but it's giving us, the table gives us the CDF values, right? Which is, if you remember, the definition of a PDF or the definition of a CDF is just the integral of the PDF, right? So this is saying like this, whatever this value is, it has the highest likelihood, right? Compared to the values in the tails that have a really low likelihood, right? Those are the different values that X can take on. And they have different likelihoods, different probabilities. And then when you sum across those probabilities, that's when you get the values that the table gives you, which is the probability or the integral of this area, right? And that's like your CDF. So just make sure you understand the difference between the area under the curve and like the actual values that X can take on, right? So let's try another one. Let's practice another one in a different kind of format. So let's say you're given a problem that already gave you these parameters, the values that X can take on, or W in this case. And it says, what is the probability that W lies between these 2 points on this chi-square distribution? It would say something like this, right? Well, let's see. Let's find on our table what these points would be. Right? We have like, I don't know, 18.5. We have 50.9.
We take this from like the spread, right? Like on the chart.
Yes, exactly. We'd go and we'd look at the chart we have here. And yeah, I'm gonna see which ones I decided to use. I think 18 point, yeah, it should be 30 degrees of freedom still. Because we're still going along with this sales question, I guess. 30. I'll make a note of that. So let's find, instead of looking for, I guess, this top part, right? Instead of looking for the probability that we want to be in like the subscript of the X or the chi-squared, we're going to find this actual value. And if we go to the table, we look, everyone watching the recording, scroll to 30. It looks like it's 0.95, right? Do you see that? It's equal to 18.4926. So this is about 18.4926. And that means 95% of the values that X can take on lie above this point, right? At random, because it's or W, it's a random variable. So this is going to be 5%. And this would be like the 5th percentile. And now let's find the other one, 50.9. Let's look for that. Looks like 50.9
Yeah, next page.
is right
There it is.
right here. Perfect. 30 degrees of freedom. And it has 0.01 probability above it. So it only has 1% above that, right? This is 1%. So this would be like the 99th percentile. Right?
So the question is, how much of it lies in between?
So how much of it lies in between?
94.
94, exactly. 94%. Right? You take 100 minus 5% and 1%. So we can confidently say that the probability that W lies between 18.5 and 50.9 is 0.94.
94% confident that the true value of the parameter W lies between 18.5 and 50.9.
Yeah, if we're doing like a confidence interval, we could use that same logic here.
Okay.
Exactly. Okay. So if we were doing like a hypothesis test, we'll come back to this, but I just want to write this out. The test statistic for this is going to be, for chi-squared, is going to be n-1 times s squared all over sigma squared. And that's going to be what follows the chi-squared of n-1, which is v, right? Degrees of freedom. And this only is true if what?
If we know what the underlying population parameter is for specifically variance, standard deviation, we have to know standard deviation true. Actually,
Not exactly. If we go, this is another very useful thing, is this flow chart, right? If I'm trying to do a hypothesis test for variance and the underlying distribution is not normal, can I do it? No, I can't, right? So we would use a chi-squared if it is normal. So that's why I'm making this asterisk here saying this only is the case if the underlying distribution follows a normal distribution, right? And you also have your X bar, which is going to follow a normal distribution. Okay. Any questions on chi-squared? Cool, cool, cool. Let's move on to T. T distribution. All right. So you might see this written like T with V again, right? V is also degrees of freedom in this case. V equals n-1. Remember that from our chi-squared. What a T distribution looks like is kind of like a normal. So if I have a normal distribution that looks like this, my T distribution is probably going to look something like this.
it's also symmetrical.
Also symmetrical, right? One thing to know about the chi-squared is it's not, which is why you have the 2 pages, right, on the table. But you're going to have thicker tails with the T, and you're going to have a lower, I guess, peak there. But as your degrees of freedom get bigger, like if you like go online and look for like some simulator, like it's really cool because it'll start getting taller and less in the tails until it like looks like a normal distribution. So basically the idea of that is as the degrees of freedom get big or as they approach infinity, T approaches a normal distribution, right? Which is why when we think about that flow chart, which is why by the central limit theorem, if we have 30 or more observations, 30 is just an arbitrary number that we decided to call large. If we have 30 more observations, then that means we can use a z, or we can use a standard normal, right, when we're running our hypothesis testing, because t is going to converge to a normal distribution. So the expected value of t would equal 0. And the variance of t is just going to be your degrees of freedom all over your degrees of freedom minus 2. And that's obviously for any degrees of freedom that are greater than 2. Or else we would have issues there. Yeah. And then kind of like we talked about, as v gets bigger, it's going to converge to a standard normal, which makes sense, right? Because the mean of standard normal is 0 and the variance is 1. What does this whole thing converge to as v gets big? Yeah, it'll converge to 1. Because infinity over infinity minus 2 is just 1. It's like infinity over infinity. So if you take the limit of that, you're just going to get 1. So that is, if you remember, your number of observations kind of determines your degrees of freedom. So that's the idea of, if I have enough observations, then it's gonna converge to a normal, standard normal by the central limit theorem. So pretty cool. So now let's practice using the t-table. Okay. So the first practice problem I have here is we're gonna find a and b so that the probability of some y between these values is equal to 99%. And the degrees of freedom, 15, we'll say. So basically, I guess one tip I have too is, if you're ever struggling to think about the distributions, you're like, what do I want? Is this above or below? What am I trying to do? Draw it out. Always just draw it out, and that'll help you organize your thoughts. Because exactly, yes. So we're gonna want 0.005 here. We want 0.005 here, which is the same as 0.5%, right? So let's find those values. Let's go to our handy dandy table here. Here we go. This is our Z. So we have 15 degrees of freedom, and we want to find, if you look at this drawing, we want to find some probability above. And if we look here, t sub 0.005, depending on the degrees of freedom, that value is going to give us the percentage. That value is going to give us the value that has 0.5% above it. Does that make sense? So that's what we'd want to be like B, for example. So let's scroll down to 15. Looks like it's 2.947. So write 2.947 here. And then A, similarly, we're going to want 5% to the left of it, right? And so what do we know about the t-distribution is that it's symmetrical, right? So A is just going to be negative 2.947. So that means that this is going to be 99% or 0.99. Subtract off 0.5%, 0.5%. This is our A and our B. We did it. So, and then your test statistic for a t-distribution test, like if you're doing a confidence interval or more like a hypothesis test, but you also use it in a confidence interval, is x bar minus mu all over the variance over n, take the square root of that, and that's going to follow a t. And this can be used when n isn't large. So n is less than 30. But x is normal. But the underlying distribution is normal. So if we go back to our flow chart here, people on the recording, let's go back to that flow chart, pull it up. We're trying to do like a mean hypothesis test, right? First question, is the sample large? If the answer is yes, we can always do it. Always run the hypothesis test, because by the central limit theorem, everything will converge to a standard normal, right? Even if it's a uniform, even if it's another kind of distribution. Whereas if it's not a large sample, if the underlying distribution is normal, and we know when we don't know the variance, the true population variance, we'd use a t, right? Look here, if the underlying distribution is not normal, we cannot run the test. We can't do it.
Okay, so we can still use Z.
If we know the variance.
Even we can use Z, even if it's less than 30, as long as we know like the variance of the truth.
Yeah, exactly. The true population variance, not the sample variance. So 2 things that I would bring up here is, one, when you're going through your test, make sure you pay attention to whether the question specifies if it's the sample variance or the sample mean, or if it says if it's the variance of the industry and you're only taking a sample of the industry, that might imply that it's actually sigma squared, right? The true variance, not the sample variance, or S squared. So I would just look for keywords, make sure you're understanding what is what. And secondly, I would try to memorize this flow chart. It's not too difficult to memorize, but just remember the different, I guess, the different key concepts that must be true if we want to run a test given certain criteria. So it's pretty easy to remember that, like, if it's not an underlying normal distribution, you can't do it, like, at all, right? Whether that's you're doing a mean hypothesis test or a variance hypothesis test, if your sample isn't large with the proportion, it doesn't make sense that the underlying distribution is normal. It doesn't make sense we ask that question because we know it's Bernoulli, right, with proportions. So that's why that's not there. But you can't do it if it's not an underlying normal distribution. So that's one thing to remember. And another thing is just with proportions, if you don't have a large sample, you can't do it, right? Because central limit theorem won't apply. So make sure you're familiar with that flow chart. You could totally have a question that's like, it looks like a real question, and maybe the right answer is you have to say, can't do it, right? Or you have to say, we can only do it if we assume the underlying distribution is normal, or something like that, right?
So you don't ever test the proportion with T. You only use Z.
Correct.
Proportion uses the distribution.
Mm-hmm.
Or the
Binomial, yeah.
binomial.
Well, I guess it makes sense.
Does that make sense?
Yeah, that makes sense, because the first question is if it's large. if it's
Yeah.
large enough. So even if you use T, it would just default to C.
Correct. Yeah. Exactly. So if you dive into this flowchart, it does make sense. It's not just random bubbles and words and information. So hopefully that explanation helps a little bit. But let's move on to confidence intervals. Okay. So a confidence interval, you might hear the language like, given the data we've observed, there's a 95% probability that the true value of whatever parameter we're testing, the true value of mu, like the true mean, like is between these two different parameters, A and B. So if I have a confidence interval of like 5.5 to 20.3, and it's a 95% confidence interval, then I could say I'm 95% confident that the true mean lies somewhere in between these two parameters, right? So if you're given a question that's like, interpret this confidence interval or interpret what this means, make sure you say that, right? That we're 95% confident, or there's a 95% probability that the true population parameter lies somewhere in between these two values we have in our confidence interval. So that's kind of what it is. Let's walk through how we conduct, I guess, a confidence interval test. It's not really a test. How do we construct one? So I'm going to pull up the homework because I think it's a good practice here. So if people on the recording want to pull up the homework, that would be great. So also, side note, when you're studying, definitely go back through the homeworks, definitely go through the lecture notes. They have problems there too. They are a great resource to practice, like super phenomenal. So make sure you go back and look at those.
What are the homeworks that that are like they haven't been tested on yet? That makes sense. That we haven't done like.
Oh, they are all of these ones. So everything I'm going over today. So homework 17 through homework 24, technically 23.
I'm just glad we don't have to state it on. And like, I have to go to the statistics.
Like code and stata. That would be fun. For some people, maybe not. Okay, but let's try, what question should we do? Let's do this one. The hospital question. So number 2. So the administrators for a hospital wish to estimate the average number of days required for inpatient treatment of patients between the ages 25 and 34. A random sample, keywords here, random sample of 500 hospital patients. So I'm just going to write down the information. This is how I do it. N is equal to 500, yeah? Between these ages produced a mean and a standard deviation. Remember, this is sample mean is equal to 5.4 and standard deviation is equal to 3.1. Sample standard deviation, which means S squared is 3.1 squared, which is just 9.61. Construct a 95% confidence interval for the mean length of stay for the population of patients from which the sample is drawn. So we need to find the 95% confidence interval. So to do this, we can use, I guess, 2 different methods. They're the same thing, but X bar plus or minus your Z or your T or whatever it follows times the standard error, right? Oh, sorry. Which is probably what I think is what we did in class. And so that your standard error is just like your sigma squared over N. But I'm going to walk you through, I think we also did this, the long way. This is the shortcut. Let's walk you through the long way just so you understand what's going on, okay? And I think this is how in class we did the variance ones. So
yeah, so it's like you have like the middle and divide it.
Exactly. Yes. So the way we set it up is all it is it's a probability equation, right? 95% confidence interval is going to be 95% probability is equal to the probability that some A, that my test statistic, if we remember the test statistic for just a mean test here is this, lies between A and B is equal to 0.95. So let's figure out what A and what B are. And how do you think we might do that?
To multiply the standard error to both sides.
That is true. But how do we find what A and B are? Over here,
Oh, because you have to find
Is a
like
hint.
on the chart
Exactly, yeah,
where 0.95 is, or 0.05 and then 0.95.
yes, exactly. 0.025 and yeah. So this Z, when we're doing this shortcut, we're doing the same thing. What we're doing is we're finding this A and this B that are, I guess, the limits of our interval, right? So here, if we're doing a 0.95 probability, we'd want 0.025 in each of the tails. So N is 500. So what can we use?
Z's.
Yeah, exactly. We can use our standard normal table. So let's find those.
0.025.
And if you don't have it memorized by now, you might. You just might soon. But 1.96. Yep. And negative 1.96. Exactly. And that's will be the case for a two-sided 95% confidence interval. And now we want to multiply this to both sides, right? Because if we're going to manipulate it here, we're going to manipulate it on the left and the right side. So it would be like 0.95 is equal to the probability that negative 1.96 times, I guess, 3.1 all over the square root of 500 is less than x bar minus mu.
So for the standard error, is it variance over n?
Yes.
Or that?
Yeah, it's going to be your S squared, which is your sample variance.
Oh, okay, but when you take the square root of that, it just becomes your standard. Standard deviation.
Yeah, your sample standard deviation. Yeah, because if you remember, variance is just your standard deviation squared. Exactly. Good job. So if I do that out on a calculator, I get. Also, I would recommend not like rounding heavily while you're doing this. Go to as many decimal places as you'd like, but try to go to more than 3 at least. I usually just do 4, but okay. It's true. Because if you do round a lot, like if I just rounded this to 0.1 or 0.14, that could change things a little bit, but not too much. But you just don't want to have rounding errors. Okay. And then when I multiply that out, plug that in a calculator, I get negative 0.27174. I'm just going through all the steps here with you so you can see what's going on when we do a confidence interval. And then we're going to want to subtract 5.4 off of the middle and on each side. So when we subtract those off, you get negative 5.67174. It's less than negative mu. Don't drop that negative. And negative 5.12826. But now we're like, crap, our mu is negative, and we want to find some parameters at the true value of mu lies in between, but this is negative mu. Well, let's just multiply it by a -1 and flip the signs, because if you remember how inequalities work, when you multiply or divide by negative, you got to flip the signs. So you can flip the order too if you want. I usually don't, just to not like mess up, but I just flip the signs. And this, once you get here, make sure you look and ask yourself, does this make sense? Because if you mess up the negative, if you mess up something along the lines, you could have like a value that's actually less than the other value, saying in your confidence interval that it's greater. So, and it's not always the case that if you just flip it, it's right. So just make sure, does this make sense? Is 5.67 greater than 5.128? Yes. Perfect. So the confidence interval, yeah. So my confidence interval would look something like this. This would be my answer on the test. I am 95% certain that mu, the true mean, right? If you remember, I only have a sample mean. What was that?
95% certain.
I'm 95% confident. What? I'm confused.
Can't say certain.
Oh, well, I'm 95% confident that mu lies in between A and B, which is 5.12826 and 5.67174.
Would you still accept the answer above? As, or would you need the,
What do you mean?
like, right above it, if you did like the probability that is in between that is equal to 9 point, I mean, just skip.
Yeah,
It's equal to 0.95.
yeah, that works. Yeah. Traditionally, a confidence interval is written like this.
With the brackets.
Yeah, not like this. But this is saying the same thing. Like in Stata, when you run your regression output, your confidence intervals look like this.
Okay.
But you're not going to get docked points if you write it like this. Okay. So that's confidence intervals. That's the gist. We just did a mean confidence interval. Note that you can do like a confidence interval for like variance, for example. And it's the same thing. You just use your variance test statistic, right? Your n-1 times s squared over sigma squared. And it's going to be a similar idea when we are about to talk about hypothesis testing. The last part of this class, we kind of just learned what a confidence interval is, how to do a hypothesis test. And then we just kind of run through the different kinds of confidence intervals and hypothesis tests you can do, right? You can do a mean hypothesis test. You can do difference of means. You can do proportions. You can do difference in proportions, and you can do variance. Differences and variances is an F test, and we won't do that. We didn't do that. So that also is how your flow chart's mapped out, right? Mean, proportion, variance. So that's all it is. It's the same thing, hypothesis test, confidence interval, just with different distributions because we're looking at different parameters. Does that make sense?
Yeah.
So don't get confused there.
We can go over, Sarah.
Yeah, we'll go over the other ones too. But it's the same process applies across the board. You'll just be using different test statistics and different distributions. Yes, but the same skill set applies. So that's the long way to do it. Once again, you can always do it this way, right? It'd just be your sample mean in this case, because we're looking at the mean. It'd be your sample, whatever, plus or minus your margin of error. On your homework, there was a problem that asked you to calculate the margin of error. Margin of error is just going to be your test, I guess your Z stat or your T stat, whatever it is, 1.96 in this case, times your standard error, right? That's your margin of error. Okay, so now let's move on to hypothesis testing. And this, I think, is the trickiest part, is just getting the intuition behind all this stuff. So a hypothesis test is basically the idea of we have data, right? We pulled some sample from the population. If you remember from last unit, we talked about sample versus population. It's super hard to figure out what the true population mean is, for example, because if I want to know like the true average age in the United States at a given time, I would have to go and ask or go collect data, accurate data on every single person in the United States, which is not feasible at all, right? So instead, what we do is we take a sample, random sample, and we try to use that random sample to be representative of the population. So a hypothesis test is basically saying,
Testing the sample. See how good it is.
exactly, it's kind of testing like how likely it is that I pull this sample, for example, given the true underlying distribution or the population distribution looks a certain way. So if you remember from your homework, you had like, actually I think this is the one we're going to go over, the KFC one, right? KFC claims that whatever meal is only 280 calories. And then they pull this sample and they find on average it's 358 calories. And so they say, hold on a second. Is it the case, right? The hypothesis test is doing this. It's saying, is it the case that there's some distribution where the mean calories of their meals or whatever is 280? And I just happened, when I pulled my sample, I just happened to pull a very unlikely sample here in the tails, right? Or is it the case that I actually am looking at like a different distribution that maybe 320 is the true mean calories for these KFC meals, right? We don't know. Maybe that's the case. And it's way more likely that I would pull this test statistic, this sample, right, from this distribution than from this one, right? And so the hypothesis test is kind of comparing those probabilities, and we're deducing kind of whether we can rule out or not whether this sample came from this population underlying distribution. So that's what's going on here, right? And if you remember, our alpha is our type 1 error. It's how many times are we going to reject the null hypothesis, even though, bless you, even though the null is true, right? So if that's 5%, that's saying I'm going to leave like 5% here in these tails. I guess it would be 2.5% on both sides. But that's the idea of like, oh, if I pull a sample that's like super unlikely on this, like look at this PDF, super unlikely, but still possible. Totally could happen. Very, very unlikely, but could happen. And so I'm saying, when I say like, let's use 5%, or the 95% significance level, like if my alpha is 0.05, then I'm basically saying 5% of the time, I'm going to reject the null hypothesis, or 5% of the time, I'm going to say, holy crap, this is so unlikely. This is probably not the true mean. So I'm going to rule that out, even though actually is the true mean. We were wrong 5% of the time, right? It is the true mean. It just was a really unlikely pull out of the hat, right? That sample. So that's what your hypothesis test is doing. That's the intuition behind it. When we have a p-value, for example, the p-value is going to be the probability that you observe that sample statistic, that test statistic, given the null hypothesis is true. So like, if my p-value is super low, that's why we reject the null, because it means that the probability that I get that test statistic based on the sample I drew, given that the null is true, is super low. If it's 0.003, like it's 0.3% likely to happen. Could happen still, yes, but so unlikely that I rule it out. I say it probably didn't come from this null hypothesized distribution. Does that make sense?
Yes.
And so that's what's going on here. So that's really, really, really important for you guys to know. Very important. Understand the intuition behind a hypothesis test. What is happening? What is a p-value? Be able to interpret those things. And we just went through it. I just defined those things for you. So hopefully that helps. But like, for example, we can get a test statistic, right, from our data. And using this test statistic, we can find a p-value. We have some alpha, always, it's arbitrary. This alpha doesn't come from the data. It's something that we as researchers will pick. So like I said, alpha is just, yeah, you'll be given the alpha unless it asks you to like reverse engineer it all and solve for alpha or something. But alpha,
Crummy statistics.
Al-
You always pick alpha before you do a hypothesis test.
exactly, it's
If you change it, then that's kind of dishonest.
it's going to change your results. Exactly.
Because
Because you could have something that's significant at the 1% level, but not significant at the I guess the 10% level, and not significant at the 5% level. Does that make sense? And then another thing to keep in mind is whether we're doing a one-tailed or a two-tailed test. You could have something, you could totally come across something like in the homework, we had one example of this. I think it was the proportions homework, where like it was right on the edge of rejecting and accepting the null. And whether you did a two-tailed or a one-tailed test determined whether you accepted or rejected the null. So if you do a two-tailed test, your rejection region becomes smaller. Granted, it's on both sides, but it does become smaller. Whereas one-tailed test, you take everything from this side and you move it over here, right? And so your rejection region becomes bigger when you're doing a one-tailed test. So
it'd be like, instead of what's the probability, or like, what's the probability that the true mean is greater than 280? It would be like, no, it's different than 280. It'd say what's the probability that it's greater than.
yeah, so a one-tailed test is going to be like your null hypothesis is going to be equal to some 280, right? Whereas your alternative hypothesis is going to be, we're guessing that the true population parameter, in this case, the true mean of the KFC meals is greater than 280, right? Supposedly maybe 320 or something, you know? Whereas a two-tailed test is just like, it's not equal to 280. Could be higher or lower, it's just not equal, right? So if I were to do like a two-tailed test, for example, or a one-tailed test, this might be my rejection region, and maybe my test statistic.
So you're doing above then.
Yeah, this is just an example to show you guys. If this is my critical value, okay, and this is my test statistic, and this is an upper tail test, then I would reject the null. But suppose I do a two-tailed test instead, and my alpha stays the same. If I don't adjust my alpha accordingly, this area, this rejection region is going to become smaller. Suppose now my critical value is right here with the two-tailed test, because on the other side I have this same critical value. Now I am not rejecting my null hypothesis, right? It doesn't lie in the rejection region. So I fail to reject. And that, the only difference here, my alpha is not changing. What's changing is whether I do a one-tail or a two-tail test. So that is also something to keep in mind. And a lot of students have been like worried about, how do I know if I'm doing a one-tailed or a two-tailed test? Just look at the question, look for keywords, right? Usually it'll say greater than, less than. If it's a one-tailed test,
Is different than would just be.
is different is a two-tailed, right? Exactly. Usually, for example, with like difference in means, usually we'll be like looking at a two-tailed test because we're just trying to see, are they statistically significantly different, right? But you could totally have like a one-tailed difference in means hypothesis test.
Key difference when you do like a difference in means, where you get like that confidence interval, is to make sure that 0 is not in the confidence interval.
Correct, because then that means that
It's possible for them to be touching, or that they overlap.
exactly, they're not statistically different. They're, even though it might be like one sample's 20 and one sample's 10, maybe you just pulled them from the same distribution and they have the same mean, right? Going back to that idea, maybe they just happen to be, if this is sample 1 and this is sample 2, maybe they just happen to be pulled from the same distribution, even though they're different values. If this is like 10 and this is 20, right? Or if they're statistically different, that means that sample 1 actually maybe is not coming from this distribution, but it's coming from this one. If my likelihoods look like this, that's probably unlikely, and I'll fail to reject that null. But that's what's going on here when we say that. So just to come full circle here to finish the thought, we use our test statistic to find the p-value, right? You can go use your table, find the probability that lies under or above your test statistic. And then we use alpha, which is an arbitrary number, right? It'll say test at the 1% level, at the 10% level, at whatever level.
50%.
That would be a terrible alpha, but it could be an alpha. And we use that to find our critical value. So we'll go straight to the table and we'll find where that probability is given based on a certain critical value. So use your test statistic, which comes from your data or your sample. Your data determines your test statistic. You have a different test statistic depending on what kind of hypothesis test you're running. and you're going to use that to find your p-value. And then you're going to use alpha, which should be given to you to find your critical value. So in order to conduct a hypothesis test, like to reject the null, either your alpha must be, your p-value, sorry, must be less than your alpha, or you can just look at your critical value and your test statistic, right? And your test statistic must be more extreme, I'm going to call it, than your critical value. Basically, the absolute value of your test statistic is greater than the absolute value of your critical value. Because if we remember our two-tailed test, if these are my critical values and my test statistic lies here, I reject because it creates this rejection region. But technically this test statistic is less than this critical value. It's more negative. Whereas here, my critical value is less than my test statistic, but I still am rejecting it because it creates that rejection region. So just note that if you're comparing the test statistic to the critical value, you want to make sure when you're rejecting, it means your test statistic is more extreme than your critical. Is on homework 19. Question 3. That's the KFC one. Perfect. Okay. Sorry for the pause. Just needed to find that. So this one says nutritional information provided by KFC claims that each small bag of potato wedges contains 4.8 ounces of food and 280 calories. So they're claiming that mu is equal to 280. A sample of 10 orders, n equals 10, from KFC restaurants in New York and New Jersey averaged 358 calories. That seems problematic, right?
Yep.
If the sample standard deviation was 54, S equals 54, is there sufficient evidence to indicate that the average number of calories in the small bag of KFC potato chip or potato wedges is greater than advertised? Greater than advertised. That suggests an upper tail test, right?
1% level.
Alpha is 0.01, exactly. So what is our null hypothesis going to be?
We don't do that.
Well, I guess it's saying like in 4.8 ounces of the wedges, like how much of it is it? Because you can't really compare, I guess, 2 ounces to 6 ounces, right? But in just 4.8 ounces, exactly. Because it wouldn't make sense if I pulled a sample of, what if I pulled the sample of 10 orders, but the sample was 6 ounces of food, right? It would make sense that there's more calories, obviously, right? So that's probably why it has that in there. But it's not relevant to our hypothesis test.
So the hypothesis is mu is equal to 280.
Yeah, good job.
Mu is greater than 280.
Exactly. Going back to this picture up here, we're like, well, what if pulling this 358 sample mean or sample calories actually isn't coming from this distribution that the null hypothesis is hypothesizing, but really it comes from this higher distribution where the mean is actually higher, the true mean is higher. So our test statistic, right, is just going to be x bar minus mu. I've written this out already. S squared all over n. So that's going to be 358. And then some people are like, but we don't know mu. How do we know what to write here? Well, sorry guys. Well, we're hypothesizing that mu is equal to 280 under the null hypothesis. So this test statistic is always conditional on the null hypothesis being true. So, because that's the whole intuition behind a hypothesis test, right? That's why we're doing it. So let's use 280 for mu because that's what the null hypothesis is hypothesizing. That's redundant. So then we'll have 54 squared all over 10. And I think this comes out to 4.567. Okay. So if we think about our distribution here, we have a test statistic of 4.567. Now we need to find our critical value. How do we do that?
It's the 0.01 using the chart.
Yeah, it's the 0.01. So let's go to our chart real quick. And what chart are we going to use?
The T, because it's sample size is smaller than 30, and we don't know the true variance of the population.
Yeah, we should use a T. Exactly. So where is this at? Here we go. I'm gonna zoom out. So T. And what are our degrees of freedom?
It's chi-squared.
Oh, yeah. Where's T?
There you
What are our degrees of freedom?
go.
9. Yeah, would it be a bad idea to use chi-square for this? Good catch. 9. And how much, I guess, what percentage do we want to lie above this critical value based on our alpha?
0.01.
We want 0.01. We don't have to split it between the tails because it's just a one-tailed test, right?
Yes.
So we're going to find 0.01 and 9, and we get 2.821. So it looks like our critical value is equal to 2.821.
Yes.
So what do?
Reject.
We reject the null.
Would 0 be the center on this?
On a standardized normal, yes. Or a T. It's also has a mean of 0.
What are we doing class?
I guess we'll have to find out tomorrow. I bet Dr. Price will have a good last lecture. He did when I took 382 from him. So, but good question. We'll have to see. So that's kind of, I guess, the process of a hypothesis test. In the interest of time, I'm going to walk you through one more. And that's probably with proportions.
Could we do regression, like 24 stuff?
Yeah, we're going to go over regression.
Oh,
So for difference in means, we're not going to do a practice problem, but note that the difference in means, your test statistic is going to look like this.
This is regression.
No, but we will be going up to regression. Started with chi-squared and with regression. This is
variance.
your test statistic for difference in means. We're still on hypothesis testing, so we haven't finished that yet. Once we finish that, we get to the last lecture, which is regression. But so that's your test statistic for difference in means. Your null usually is going to be like x bar or y or mu1 doesn't equal mu2, for example, which implies that mu1 minus mu2 does not equal 0. And your alternative would be like mu1, or sorry, this equals 0, and your alternative would be that they don't equal 0. The difference between the two don't equal 0. So to rephrase that less confusingly, if we're doing a two-sided hypothesis test for like a difference in means, for example, you might see it written this way, or you might see it written this way. Same thing. We're going to hypothesize under the null that the means are the same. The true means the same, meaning if we take the difference, it's 0. And our alternative hypothesis would be that they are not the same. Or if we're doing a one-sided test, it might be like this mu1 minus mu2 is greater than 0, which would imply that mu1 is greater than mu2. So it just depends on what test we're doing. So that's how you can do a difference in means. Okay, moving on to proportions. A few things to note about proportions is like your p hat is the same thing as like your x bar, what we've been thinking about. Okay, and the mean of your p hat or your sample proportion, if it has a hat on it, it's the sample proportion. If it doesn't have a hat on it, it's the population proportion, the true population proportion. That can be thought of equaling mu or p. And then the variance of your sample is equal to the true p times 1 minus p all over n. And that's because if you remember, sigma squared is going to be equal p minus times 1 minus p. And this is like throwback to Bernoulli. This is where that comes in handy. So your test statistic for a proportion hypothesis test or confidence interval. The reason why I wanted to show you how to do confidence intervals like this way is because what we're doing is we're putting our test statistic in between our parameters. Whereas when we use this shortcut, we're not doing that. And so the test statistic is the same for a confidence interval and for a hypothesis test, depending on what kind you're doing, just FYI. So keep that in mind. So your test statistic for just a one proportion test, right, is you're gonna take the sample proportion minus the true proportion, the square root of p minus 1 times 1 minus p all over n. If you're doing a difference in proportions, so same intuition that we just went over with the difference in means, you're gonna have a sample statistic that looks like this, or a test statistic that looks like this. And then you might be tempted to do this.
Oh, good.
And this is unpooled, right? But under the null hypothesis, we're proposing that P1 and P2 are the same. So we can pool those. That's why we can pool, because of the null, right? Your null would be like P1 equals P2. So instead of this, we can rewrite it as this. And that's our P pooled. And in order to find that, we're just going to take all the n's and all the p's from before and smash them together and find an overall proportion. So if my proportion before, like P1, if it was equal to 25 out of 100, and P2 was equal to 30 out of 500, to find the P pooled, I would just do 25 plus 30, all divided by 100 plus 500. Does that make sense? And then for variance,
Oh, sorry,
yeah, sorry. No, you're good. A good practice problem that I have for you guys on this one, but we're not going to go through it in the interest of time. And it's exactly kind of like what we just walked through, just plugging in numbers to do it, is on the lecture notes with France and the US and the employment rates. So go check the lecture notes and make sure you understand that practice problem. Then last kind of hypothesis test or confidence interval we can do is variance. So we already talked about our test statistic, right? It's going to look like this. And that's about all I have for you on that. We'll do a practice problem real quick. Let's say I don't know where this practice problem comes from, but I'm going to give you the information. N is equal to 20. The true standard deviation is equal to 10. The sample is equal to 12. I actually think this comes from your homework. Yes, this is problem 3 on homework 22. So aptitude tests should produce scores with a large amount of variation so that an administrator can distinguish between persons with low aptitude and persons with high aptitude. Okay. The standard test used by a certain industry has been producing scores with a standard deviation of 10 points. A new test is given, excuse me, to 20 prospective employees and produces a sample standard deviation of 12 points. So the industry or the population is proposed to have a standard deviation of 10 points, which is why sigma is equal to 10, whereas a sample of just 20 students or 20 employees is equal to 12 points. So the question is, are scores from the new test significantly more variable than scores from the standard? And they say alpha is equal to 0.01. So this implies a two-sided or a one-sided hypothesis test. What do you think?
Two-sided.
Two-sided is
Asking is significantly more variable.
Variable doesn't tell us what direction.
It's asking if the new test is significantly more variable. Exactly, it'd be a one-tailed test, right? Does that make sense? Yes. Because it's asking if it's significantly more variable.
So we're looking at the standard deviation or the variance, and we're trying to see if the variance is greater or less than what it is. And because we're saying it's more variable, therefore we're looking to see that the standard deviation is greater, meaning there's a greater spread.
Exactly. So basically the idea is the industry is saying, oh, the standard deviation is 10, but in the sample we have, it's actually 12. So that leads us to believe, does this mean that the true standard deviation is actually greater than 10? Or is it just the case that I happen to draw a sample of 12 on that distribution, right? Where the true sample standard deviation is 10. Does that make sense?
Yeah, we're comparing, so it'd be like, it would be the sample variance over the true variance.
Oh yeah, for our test statistic, yes, exactly.
Times that by degrees of freedom. For n-1.
Yes, that's the degrees of freedom. Yeah.
And this would just be from the sample.
Yes, exactly. And this we're going to use a what distribution? With a variance hypothesis.
Oh, that would be the chi-squared.
Exactly, it'll be chi-squared. Yes.
Because why? Because chi-squared is the square, just like standard deviation squared is variance.
Yeah, you got it. So our hypothesis, so this means that that sigma squared is equal to 100 and that s squared is equal to 144. Okay, so our true hypothesis or our null hypothesis is going to be that the true variance is equal to 10. Oh, yes. Is equal to 10, whereas the alternative hypothesis, right, we're doing upper tail test because it says we're trying to see if it's greater than this. Is it greater than 10? Or 100, sorry. We squared that standard deviation. So let's find our critical value. Okay, well, we want 0.01. This is actually going to be a chi-squared. We want 0.01 to lie above this critical value. So let's go to our table. Let's find chi-squared. 0.01 with our degrees of freedom, 19, 36.19.
Alpha?
Alpha is 0.01, right?
Oh, okay.
Because if you look at this picture, whatever the subscript on this chi-squared is the probability above that parameter, that number that X can take on. So at a degrees of freedom of 19, under this with 0.01 above, right? That means there's 1% above this value in probability. We're gonna get 36.1908. If you find that on your table. If you're watching this recording and you're struggling to find these numbers, email me and I can do my best to help you. Or stop by our lab hours. I think Wednesday is our last day. Because the last day of class.
Okay, I need to bring cookies or something like that.
No, you don't have to. It'd be very kind of you though.
What time is it? For your lab?
I'm in 12:30 to 2:30. So our test statistic is, like we said, n-1 times s squared all over sigma squared, which if we plug that in is just gonna be like 19 times 144, all divided by 100, which is equal to 27.36, which lies like right here. So what do? Do we fail to reject or do we reject?
What are the numbers? Show me again.
144 divided by 2.
This is our test statistic.
Oh, that would be 100. So we failed to reject.
Exactly, we're gonna fail to reject. So what does this mean in the context of this problem? It means that it's probably the case that we just drew a sample with a standard deviation of 12, even though the true mean or the true sample, the true standard deviation is probably 10. It's likely, right? It could happen. It's super likely, so we can't rule that out. If we were to fail to reject the null, we'd say, actually, the true standard deviation of the population or of the industry is actually higher than 10, probably. We don't know for certain, right? We have that, in this case, we have that 1% of type 1 error that could be going on here. But that's what we would be saying if we rejected it. And so that is an example of a variance hypothesis test using chi-squared. Okay? So that is all for hypothesis testing, right? We have all the different kinds of hypothesis tests we can run. I suggest if you are given a hypothesis test question, just make sure you clarify it then, just like reject or fail to reject the null and why, right? And you can always catch yourself too. Say you find some p-value that's lower than your alpha, and for some reason you write fail to reject the null, and then you say because, if you write this out, you say because p is less than alpha, then you'd be like, hold on a second. You'd catch yourself and you say, oh no, I'm rejecting this null hypothesis. I've seen several times where people will say, oh, we reject the null because, you know, our test statistic is more or is less extreme than our critical value. And I'm like, hold on a second. You did everything right. You just came to the wrong conclusion. So I think one of the biggest helps on doing well in these exams is reading the questions carefully, drawing a picture, and just checking your work. Do all the calculations in your calculator. Like you don't want to miss. I don't think so. But it's in the testing center, so I don't think so. But you don't want to like lose points because you had everything right and all your work was right up until the point you plugged it into the calculator. You know what I mean? So just double check it. It happens all the time. Something will happen and you'll lose points for that. You'll get partial credit for sure, but you'll lose points for not having the actual right answer. So just be careful, be cautious. It's okay to go through things slower. It's okay to go through every single step if you're doing algebra. I know on like the PDF for joint and continuous functions and stuff like that, that's also important. So just please keep that in mind. Okay, so regression. Let's go through regression. The intuition for regression is this. We have a bunch of data, okay? And we want to fit a line to this data. So how do we do that? We can use OLS, which we did the proof in class. I don't think you'll be expected to regurgitate that proof on the exam. So I would not stress about that, but it's definitely fair game. Like he talked about it in class. It's in the lecture notes. Like he definitely could ask you a question on that, but I don't think he's going to ask you to regurgitate that, because what's the most important thing about regression is understanding what's going on and not necessarily like the math behind the proof. You know what I mean? So we have some y. What is y? Y is the outcome. Exactly. And then we have some x. I could totally see you having a question that he won't tell you which one's which. You have to know which one's which, right?
Just based on the wording.
Or the variables, right? X is something you can choose, right?
Why you can't choose.
So like, for example, education on wages, maybe. Like, I can't necessarily like choose my wage.
Test scores, hours study.
Exactly. The score on your test, you can't exactly choose it directly. You can choose different factors that will impact the score you get on the exam, but you can't choose directly your test score. But you can, that was a great example, you can choose how much you study, right? The number of hours you study. So that would be like your independent variable. So we're going to try to fit a line to this, and we're going to use OLS, which, what is OLS doing? It's basically taking these errors, squaring them, and minimizing them, which makes sense, right? You're going to find some line that has the least amount of deviation, basically, right? The sum of all the deviations from the line, and we're going to minimize it. And that's what OLS is. So it's going to fit this line. And so I have actually some y. Like this is what I actually observe. Whereas this is my predicted y, right? By the line. And so this difference here is my error. Does that make sense? So if I plug in some x, let's say x is 20, okay, and whenever x is 20 in my data, y is 10, but my line, the line I have, my y equals mxb, mx plus b line, or y equals beta naught plus beta 1 xi line, this is equal to, actually, it's equal to 8, for example, right? So basically, if I plug in 20 into here, I get 8 out of here, and that's my predicted y. But my real y I observed wasn't 8. So what's up with that? Well, that's where we get the error, right? And that's why we say, well, y, not y hat, y is your actual outcome. This would be like 10, and this would be 8, is equal to the true beta hat plus beta 1 times xi plus some error, right? Which in this case, your residual would be 2. And so that's what's going down with this, with regression. That's what's happening here. Does that make sense? So you can be given questions that maybe ask you to calculate different values of x or different values of y based on certain values of x, find the residuals, and find beta 1, find beta naught. If you remember, beta 1 is going to be equal to the summation of xi minus x bar times yi minus y bar all over the summation of xi minus x bar squared, which is the same as the covariance of xy all over the variance of x, which is also the same in class we talked about. It's the same as like the correlation coefficient times
Rise over or
the standard deviation of x over the standard deviation of y.
is that right? Or no, I think
Is it flipped?
yeah, it's rise over run.
I think you're right. Yeah, because one of these x's goes here. Yes, I think that should be right. But we can also check the lecture notes too.
But that's how I'm going to be calculating it on the test.
Really?
I'm not going to play with the PU1 equals a sum of this and that.
Interesting.
Oh, man, I'm calculating it. I'm
I would
calculating
do
it.
both ways, just to check my answer.
I would say the best way to calculate it is probably the first way, but maybe that's just because I'm used to that.
It's like a. It was like for the it's like a name tag, and then I just blanked it out. So
Here.
I need to get more B-weight cloths for that. Like I want a sweater or like a hat, t-shirt.
Okay, let me just go down. So one thing I would say would be good for you guys to go over. We're not going to go over here, but I would recommend going over the last problem. I think there were only 2 problems, but go over the last problem on your regression. Homework. No, on the homework, the regression homework, go over the last problem. That was a really good problem. And maybe practice going over it by hand. I know a lot of you guys did Excel, which is great. But unfortunately you don't have Excel on the exam. So I would practice maybe going through it by hand, which is why I wanted to pull this up too. So we're going to go over just the last example on the lecture notes in regression. So if we're given some data, we want to find like beta 1, beta naught, right? We want to find the slope and the intercept of our line. So let's find some slopes, or let's find some averages is what we're going to do first, right? So we can take the expected value of X and the expected value of Y. Remember that in discrete cases, the expected value of X is just going to be like the weighted probabilities, or the weighted average by probability. In this case, if each one has the same probability, you just take 1 over n times the summation of xi is your x bar. Same thing with y. And so we get 0.09 and 0.606, right? And so now that we have our x bar and our y bar, we can find our beta 1. So I can take like each x value right here and each sample mean, which is x bar, which is going to be the same across, and I can calculate that. So in this case, my beta 1 would be like, the summation of xi minus x bar would look like the following. I would take xi, the first one, which is 0.08 minus 0.09 plus 0.09 minus 0.09 plus 0.1 minus 0.9. And this is just like x1 minus x bar, right? And so on. And we just have 3 observations. So that's what that is. And you do the same with y. And then once you have those, you multiply them together. And then you can also do the same thing with your variance. And I guess one thing is this summation applies to the x and the y. So let me correct myself here to not lead you guys astray. I would need to take my y values too. So y is the first y1 minus 0.606, which is y bar. Then add this product to my other ones and so forth. So this is actually wrong. Don't do it that way. Similarly with x, the summation of xi minus x bar squared, I'm going to want to take 0.08 minus 0.09, right? x1 minus x bar, if we remember, and square it, and then add that and so on to like all the other observations I have. And that's how I can get beta 1 is I'm going to take this, divide it by this. And in these lecture notes, when we do that, yeah, go ahead. What was that? Oh, this shouldn't be negative, no. Yeah, no, I copied that down from the table wrong. This is not negative. Good catch. So beta 1 is just going to be equal to 6.25, for example, in this case, if you want to check your work there. But it's really simple. We just subtract the x mean off of our x's and multiply that times the y mean off of our y's And we do that for each observation. So we don't do it all first and then multiply. We do it for each observation and then we add them up, right? And then we take both those sums and then we divide them. And that's how we get that. Then if you remember, beta naught is equal to what? True, it is the intercept. But what is our beta naught equal to?
Oh, it's x times b1, beta 1.
Exactly. So this is our beta naught. So once we have our beta 1, we can plug that into our beta naught. And these are bars, sorry. Our average. And we can plug in our average for y and our average for x and get beta naught is equal to 0.0435. This is how I would recommend solving for beta 1 and beta naught. And then once we have our line, right, we can write our line out. It's going to be y is equal to 0.0435 plus 6.25 x, right? And so if you're given a problem that had you solve for beta 1 and beta naught, and then it said, suppose x equals 20, what do we expect y to be, right? And that would be plugging in 20 here. What is y? What does it shoot out for y, right? And note that this is the line. So if we have our data, this is giving you the y values on the line, not the actual y values. This is giving you the predicted y values or y hat, okay? And then if it asks you to find the error term, how do we do that? We're going to take our predicted y's and subtract off we're going to subtract off our predicted y's from our actual outcome y's. So like, for example, here, I would take yi minus y hat I, and this is going to equal my error. Similarly here.
So it's expected minus actual. Or
Yeah, it's expected minus actual.
one's greater. Or
This should be a hat. There we go. This is actual minus expected, not because y hat is expected.
so it's okay.
So it's this actual value.
It's the y.
Yes, y hat is the predicted value.
And then just the regular yi is the observed value.
Correct. And that's because, like, for example, if you remember, yi is equal to some beta we estimate times some beta 1 times x, right? I guess x wouldn't have a hat. Whereas y, the true y, is equal to this plus some error, right? So it should be the case that if I have my predicted value and the question tells me what the real value is, and I already know what, if I have my error, I can add that on to this and get this, right? This holds. So you might be given another problem that asks about the errors, and how I would go about it in this problem here on the lecture notes. I think it is a great example. I would make a table, have your x values, your y values. Without the hat, that's the actual true outcome. Whereas these y hat values are the ones on your regression line, right? These aren't necessarily on the line. In fact, you can see how they differ from the line. This lies above the line because our error is positive. This lies below the line. This is negative error. And the difference between the two is our error. And that is about it for regression. Be able to manipulate the equations to find beta naught, beta 1, be able to plug in x values to find the predicted y values, be able to find the residuals. know the difference between the actual outcome versus your predicted outcome. Why? The residual is your error. So it's the difference between the y you actually observe and the y you predict based on the line, or y hat. Does that make sense?
So say you got a value for one or something like that, x equals one, and then you get your regression equation, and then you plug in one. And whatever you have for that y variable, compared to the original y variable when x equals one, that's the residual. It's the
Mhm.
difference between those. It's how far away that is.
Exactly.
And then you're that, I suppose in this case, 3 different times.
Yes.
That's kind of how you get the total.
Exactly.
Or I suppose you look for the expected value of it, which is a really funny way of doing it, but the expected value should, of course, equal 0. Hopefully.
Yeah, the expected value of your error terms should equal 0. And if you look at the lecture notes, it also has that kind of proof here with this problem. So if you're given a question that's like, show that the average of the errors is equal to 0. You can add up all the errors, take the average, and show it's equal to 0. Or you can also show like the covariance is equal to 0, because we know that the covariance, sorry, yeah, exactly. The covariance of x and our error term is just going to equal the summation of xi minus x bar times ei minus e bar, like that. And we can plug in this as well. And we know that this is equal to 0. We want to find the covariance of that. So that's how you would do that. And that's about all we have today. Feel free to shoot me an email if you have any questions. Stop by the lab on Wednesday or Tuesday. Spencer's in the lab Tuesday. You guys got this. You guys are capable. You can do hard things. You're smart. And we're here to answer your questions if you have any. But super proud of y'all. 378 can be tough. So good job. Study hard. It'll come in handy. And once again, don't feel bad. Just reach out and ask questions. Happy to help. So I'm going to end this recording, and good luck, everybody.